over 2. C1 is equal to 0. You can drop it. So now plus by C2. Okay. And then this is our equation number 2. Okay. Then we're going to implement our boundary condition where x is equal to 0. M is also equal to 0. And we're going to substitute into equation 2. So again, this is 0, 0, 0. Okay. I forgot the minus down here. Plus by C2. So therefore, C2 is equal to 0. Okay. So from here, M as a function of x is equal to minus 2000 x cubed over 6, right? Minus 6000 x squared over 2. Okay. And this is your equation 2a. Why 2a? Because the root equation is equation number 2. So anything changes very similar to the equation, you call it 2a. Okay. So from here, that's it. Okay, that's it. So now you can you know your function. You can now sketch. Okay, so we're going to sketch our shear force and bending moment equation. Okay. So this is your x distance. Okay, so you have 0. So you have this can be V or M, okay, depending what you use. So let's look at the first equation. Let me copy the first equation. I'm going to ignore the C1 because it's going to be the C1 we found is equal to 0 already. Right. So we know at 6 we need to find the ending, right? So at 6, so V at 6 is equal to minus. So we just substitute. Right. So this will be equal to 6 squared times by 2000 divided by 2 plus by 6000 times 6 is equal to 72,000. Okay. So my 72. Okay, so let's say, so I'm going to sketch 72. So this is our 72. Okay. So this is our shear force diagram. Right. And it is a second order polynomial equation and it's set phase. Okay. So this belongs to here, this equation, and is equal to minus 72. Okay. At 6, distance 6. And then our next equation, which is M as a function of x is equal to minus 2000 x cubed over 6 minus 6000 x squared. Okay, 6000. Okay.
Where
So
did
from
the
here,
72,000 come from?
hey,
Where did the 72,000 come from?
I just substitute everything x as a x is equal to 6. Hello.
Mm-hmm.
Okay, so that's why. Oh, it's minus. Yeah.
Oh.
I forgot the minus.
So it's not, it's divided by minus 72,000.
Divided by minus 7. No, it's equal.
Oh, okay. I understand now. It looks like a divided sign.
Oh, oh no, no. So from here, so we have minus 6000. Okay, 6 cubed divided by 6 minus by 6000. 6 squared divided by 2. So this will be equal to 2000 times by 6 power 3 divided by 6 plus by 6000 6 squared divided by 2 is minus 180,000. So minus 180,000 is somewhere around here. It's a third order polynomial, but the highest function, highest order is still minus, so it still shows a set phase. Okay. So this is our minus Newton meter. Okay. Right. Okay. So as I mentioned, the only thing that we know is that x is at 6. This value is the highest. Now, I'm going to go back again, right? I'm going to circle this. Now, these are not boundary condition at all. We know it's the maximum, but it's not a boundary condition, okay? It's just the trend, okay? Now, question for you, why in a cantilever beam, this is nothing mathematical, okay? This is physics, okay? Or observation. To simplify things, this is simple observation. Why do we mention, or I'm teaching you now, not I, that's why you know now. Why do I mention for this way of distribution, right? B is where the shear force and bending moment will be maximum. Anyone? I repeat again. Why do we think? Yes.
Because it's cantilever.
Yeah. So what if it's cantilever? Why is it maximum at point B?
Because x is maximum at B, because bending moment is load multiplied by distance.
No.
Because that's where your failure would occur?
Well done. Okay. Because failure will occur over there. Okay. Now, this is only true, right, when the distribution is the maximum where the beam is fixed in. Okay. That is the only case that is true. Now, I want to go back into this sort of mathematical expression with you guys. Okay. I want to go deeper than that. Okay. Now, if the same structure occur, I know this look messy now. Okay, this looks messy now. So what if we have the same thing? The load is still look the same, but now it goes like this. Right? What if now it's not it's not a cantilever beam? It is simply supported. So this is x is equal to 0, x is equal to 6, Vm theta y. Vm theta y. Now, question for all of you, what is V equal to? We don't know. Now, what is M equal to on x and 6? On x and 6, on 0 and 6?
Zero.
Okay?
Should be max still, no?
No, it should be 0. Why? Because if I remove A, the structure will rotate. If I now remove B, right, the structure will rotate the other way. Right? So that's why the moments are equal to what? 0. So what we have just done, okay, what we have done, so we came up with an expression, okay, we came up with an expression where we have what? The equation is 2000x plus 6000, okay, or minus 2000. Okay, so we have an expression on both equation where dv over dx is equal to minus, wait, let me look at my function, minus 2000 x and then minus 6000. Right? We started from here, right? We started from here. Okay. I know it's a bit messy, but I want you to see this. Okay. What do I mean by the function changes? So for cantilever, right? Our function was what? When x is equal to 0, right? Or I'll write this out. When v is 0 at x equal to 0, this is 0. And when moment at a distance 0 is equal to 0, right? This is what cantilever. Simply supported, it changes, right? When the moment is at 0 is 0, and when moment is at a distance 6, it is what? 0. That is why, okay, math is a language, yes or no? It somehow we look at here, right? This is a language, right, where we have a mathematical expression to express what we want in terms of math. Okay, so that's why in math these are given, but it is a language. It has a meaning when you put a situation like this. Okay, and when you do your math course in strength of material, by looking at the figure and by looking at the, not just looking at the figure, knowing the physics, what will rotate, we set what? Boundary conditions. Okay, so I rest my case why it's not procedure based. A lot of analysis, okay? And it's well known once you pass strength of material, or I teach in mechanical engineering, structure analysis. Once you pass this course, okay, the degree is as good as yours. Okay, or I will say better, other courses you will find easier because now you're trained to analyze or been introduced to analyze. Okay. By the way, I'm saying this not because you all did badly for term test 2. Okay, I briefly look at the grades on some of the question is marked. It looked pretty good. Okay, I'm relieved. Okay, I deliberately now, okay, draw a line in the center, and I'm going to show you what if we were to use our old method. When I say old method, we are going to use positive shear and positive what? Bending moment. Okay. I want to show you guys the difference between the approach now. Okay. And try to convince you that once you know this method, okay, is so powerful. But the problem with this method is mathematically, okay, you have to know what is going on in terms of boundary condition. Okay, in terms of boundary condition. Now we're going to use the other method, which is what we have learned before. I mean, not really learned before, but there's an extra step, and it's not a difficult extra step. Okay, so we're going to use positive shear. And positive bending moment approach. Okay. So when we look at this again, we have point A. Right. So I'm going to, because of space. So this is a point A. Point B, right? Cantilever. Right. Then we have 6,000, 12,000. Right. Then after that, we construct our free body diagram. We know at point A there's nothing. Point B, we know there is a BY. Okay. And then we know there's a moment at point B. Right. So we are going to find our equivalent load. Right. Can anyone tell me what is this distance? Anyone?
Can you not just assume that load to be unevenly distributed with a gradient load? Like
No.
you could have a
No,
Could
the
you not-
function the function will not be the same.
okay.
You can still solve the problem. Okay, if you just want to solve the problem, yes, but you cannot